শুনতে পাচ্ছি না। ঠিক আছে, ঠিক আছে। Good afternoon, everyone, and welcome to the seminar once again. I am really thankful to all of you for your continued engagement. I would now like to introduce our third and the final speaker of the day, Dr. Samriddhi Sankar Maity. Dr. Maity has completed his PhD from IISc Bengaluru on astrophysics. He is now going to pursue his postdoctoral research work from Georgia State University and National Aeronautics and Space Administration, or broadly known as NASA. Today, he will speak on the topic, A Tale of Magnetic Mayhem, the Sun's Atmosphere and Explosive Event. So, without any further delay, let's have a big round of applause for Dr. Maity.
sequence star is the G-type main sequence star, and it's a 4.6 year old. It's actually completed 50% of its life cycle, and they primarily made of hydrogen and helium, and the rest few percent are of the iron and the other heavier metal. The core actually generates energy due to the nuclear fusion, and 99% of it via PP chain, and the last 1% is via CNO cycle. Now, what is the main sequence star, or what is the G-type main sequence star? So, if we plot the temperature with the luminosity of any star, we will get HR diagram. So HR diagram basically shows the life cycle of any kind of star. Our sun is lying in the middle. It's a G-type star, G2. So G2, and it shows the absolute magnitude, which is the proxy of the luminosity. Now going to the other morphological details, like the surface temperature of the sun is 5,700 Kelvin. On the other end, the core, the temperature is 50 million Kelvin. The mass is approximately 2 into 10 to the 30 kilogram. The radius is 7 into 10 to the 8 meter. And the luminosity is 3.84 into 10 to the 26 1. Now, these are basic information about the sun, and we people mostly know about it. So now we have to go to further details about the sun. This is the rough structure of the sun, and if we see, the sun actually has two parts. One is the inner part and one is the atmosphere. So the inner part is actually further divided into three parts. One is the core, the other is the radiative zone, and the most outer inner part is the convection. Most importantly, there is a line called tachocline. Tachocline is actually differentiate the radiative zone and the convective zone. So tachocline is very, very important. In further slides, we will go through it, and we will learn what is the importance of the tachocline. One more important thing is that in the radiative zone, the photons actually passes through radiatively, and in the convective zone, those photons passes due to the convection. The time scale for a photon to pass through the radiation zone is actually million years, and very few protons is actually pass the radiative zone to the convective zone. And in the convective zone, the hot gas actually goes upward and the cool gas goes down, and those are further interact with the photons as the cycle go on and go on. And this flow will give the surface temperature of the sun. Now, these are temperature and density profile inside the sun, and we see that temperature is decreases as we go through the surface of the sun, and similarly the density. So the most of the density is accumulated near the solar core. Going to the solar atmosphere, which is the most interesting topic in today's talk. They are further differentiate into mainly three parts. One is the photosphere, one is the chromosphere, and the other part is the corona. So corona is the outermost part, and it actually starts from 2,220 kilometers from the solar photosphere, and it's elongated and it's never ending, basically in terms of the solar system. The temperature of the photosphere is approximately 5,700 Kelvin. On the other end, the temperature of the chromosphere is 10,000 Kelvin, and in the corona, the temperature is 1 to 3 million Kelvin. So this actually gives one important question, that at the core, of the sun, the fusion creates energy. That energy passes through the surface of the sun. So there may be some dissipation of the energy going on, and so the surface will have lesser energy than the core, which is correct. But then in the atmosphere, the energy will be still dissipated, and the temperature will show a lower value. But unlikely, we see that the temperature actually increases from the photosphere to the corona. So there is an open question in solar physics, though scientists suggest few solutions, but still the problem has not been yet solved. Now, if we see the temperature and density profile of the photosphere, chromosphere in the corona, we can see one abrupt change in the temperature during the region which is not of the corona or the chromosphere. This is called the transition region. In this case, the temperature and the density actually abruptly changes. Now we completed solar atmosphere. Now we go through the most important thing, the few observational characteristics of different parts. So these, when we observe the photosphere, these small things we call the granules. So we can see those are created and those are deleted simultaneously every time in the solar photosphere. Similarly, in the chromosphere, the main important thing we see is that grass-like structure. These are known as the spicules, and the spicules is actually one of the most interesting features people now study. And not last, the corona. Corona is the main place where the most energetic events, the coronal mass ejection, happens. So with the naked eye, we can't see the solar corona, but at the solar eclipse, when the moon opaque the sun, we can see the beautiful corona of the sun, and these are nothing but the plasma which is frozen in due to the magnetic field lines of the sun. We will go through the eruptive events detail in next few slides. So first of all, one of the most important thing we know is the sunspot. From the childhood, we will know it. So these are 1989 August 2 solar image of the photosphere, which is fall on the cycle 22. We will go through it, why it is called cycle. So these yellow and blue points are polarity region of one sunspot. And if we closely see the sun, and if we differentiate the two parts by the upper part or the lower part, the northern hemisphere and the southern hemisphere, we will see that in the northern hemisphere, if the blue part, say the positive polarity region, is in the right side or in the direction of the sun's rotation, in the southern hemisphere, it shows the totally opposite feature, like the leading polarity is the negative polarity. So in a specific cycle, northern hemisphere and the southern hemisphere, the leading polarity region are opposite to each other. These law or these observational law is known as Hale's law. And similarly, in the next solar cycle, if we check in the cycle 23, we see that the northern hemisphere actually shows the opposite polarity at the leading edge. And similarly, in the southern hemisphere, the opposite polarity is the blue. But at a particular cycle, northern hemisphere polarity and the southern hemisphere polarity, the leading edge polarity are opposite to each other. This law is known as the Hale's law. Now, if we see the angle it makes, the angle between the positive polarity and the negative polarity of a particular sunspot in a particular hemisphere, it shows one inclination, and the inclination increases as we go up, as the latitude increases. From this figure, it is not actually positively seen, since we are seeing from a long distance and a large number of sunspots. But when we only focus on a particular sunspot and calculate the inclination angle, we can see the inclination increases as we go up or as we go down. This law is also known as the Joyce law. But from this figure, we can't estimate the inclination angle. But now the main question comes that why every cycle shows this kind of behavior. So this is due to the magnetic activity of the sun. This is one of the global magnetic structure of the sun. There are few closed lines like tight string-like structure. Those are magnetic field lines, and the other colored lines are open loop structure. So they are not close to the sun, but since it's a closed system, the cosmos is closed. So there are no open field lines. So it should interact with the other field lines of other planets, like it may interact with Earth and connected to the Earth's magnetic field. Now, the changes of the different polarity region at different cycle is due to the solar dynamo. So, dynamo is one of the most important thing in stars and also in planets. Our planet Earth also shows the dynamo effect, but the mechanisms are slightly different. But we will mostly focus in the dynamo case for the sun. So what happened? So we initially thought, at any time of extinction, suppose we thought the sun's magnetic field is poloidal. So the term by poloidal means the magnetic field lines are actually passes through the poles of the sun. And please consider this. This small circle is the sun, and this is also the sun. But this part is the convective zone, and this part is the core and the radiative zone. So this inner bright circle is the tachocline. So I said in the earlier slide, the tachocline will come in the next slide, which is one of the most important things for the solar dynamo. So in the tachocline, the sun actually rotates differentially. What does it mean? It means that the core and the radiative part moves in a different angular velocity, and the upper part or the convective part moves with a different velocity. So there is a differential rotation. So we can assume that at any instant of time, suppose the sun's magnetic fields are poloidal, and since the sun is moved from western direction, the magnetic field lines are frozen into the plasma, and it's winding about the around the tachocline. So now this poloidal structure will give rise one toroidal-like structure. So this effect we call it gamma omega effect. Now there are actually two mechanisms for getting the toroidal field lines back to the poloidal. Since that few scientists believe this is due to the alpha effect, and few scientists still believe that this is a BL mechanism. But mainly the ideas are same. But I actually believe BL is more positive than the alpha from the observation point of view. Now, what happens in the alpha, that when the fields are toroidal, there are some turbulence in the convective zone. Since the low density gas particle goes up and the cooler gas goes down, it will create some turbulence, and from that turbulence, the frozen in plasma will also move, and the magnetic field embedded in the plasma cells are also shows this turbulence behavior. And since this turbulence behavior is happening in the full sun, and at every small part, they create a eddy current type of magnetic field, and all those small magnetic structure, magnetic pockets create a total net poloidal field. But if we see the BL mechanism, what happened? They said that the gas particle actually goes up to the photosphere and they create a sunspot, and the sunspot will connect the field lines further. And there is a meridional flow which actually moves from this part through the pole to the tagok line to the equator and comes in. So this meridional flow will give a net toroidal structure. So these both alpha and BL mechanism gives the toroidal gives the poloidal field from the toroidal structure. So we will may guess that both of the mechanisms are correct, since we can't go inside to the sun's interiors and study it, but there is solar heliosseismology who actually Doppler scan the solar surface, and they predict few models which goes through the observation, and this is the most scientific solar dynamo picture we get at 2025. Now, this type of poloidal to toroidal to poloidal and further toroidal gives a solar cycle. So, and people studied that this actually takes a total 22 years to get a full cycle. That means from the poloidal to toroidal to poloidal. So, at every half of the solar cycle, that means after every 11 years, we can see that this type of thing, that the polarity part of a sunspot actually changes. So from 1989 to 2000, there are more than 11 years of gap. So this 11 years is called the solar cycle. So right now we are in the 25th of the solar cycle. This is the last solar cycle, and the solar cycle and the sunspot number are very correlated. So at the peak of the solar cycle, that means after every 6 years or 5 to 6 years, the number of sunspots are larger than the rest of the time of that particular cycle. And this number of sunspots is actually correlated to the active region. So basically, sunspot gives rise to the active region, and those active region gives rise to the solar storm or CME. So to study the CME, the number of sunspots present at that particular time is very important. Right now we are 25th, and there are several solar dynamo model who predict what will be the number of sunspots at a particular date. At least not accurately, but one estimation they can guess. So this is from the SWPC, the Space Weather Program Center of NASA. They predict one of their model. This is the last cycle, 24. This is the current cycle, 25. We are now in 2025, April 10th. So this is actually we are present. So luckily we are in the peak phase of the solar cycle, and if you are actively study the solar news, we can check from December to 2004, we actually getting at least 2 or 3 CME every week or every day or every 2-3 days. So now we are going to a peak phase of the 25th cycle, and it is actually good for the solar physicists. They will get a large number of data to study. Now we will go to the main part, like the solar storm. So what is the CME? Okay, I think I put some different slides in different parts, like just open few slides first. Okay, just add few things first. Okay, I think these slides will go at top. Sorry for this inconvenience. Just allow me a few minutes. I will skip those slides. Okay. Yes. So for the solar explosive events, which are correlated with the number of sunspots, the two main important explosive events are flare and the solar coronal mass ejection. So they are correlated actually. We will see in the next slide that the flares are nothing but the sudden increase of the light. It is the emission of photon particles, and on the other end, CMEs are plasma clouds which are embedded by the magnetic fields of the sun's corona, and they emit the charged particles. And flare also emits particles, not only the photon, but they are mostly neutral. They are X-ray particles, and there are two types of X-ray: soft X-ray and hard X-ray. And we all know about this type of X-ray from class 12, I think. So now these two types of explosive events are actually correlated. They are associated with it, and there is a simple cartoon structure like it. So if we see that this is one of the structure of the CME and the flare. So this is the flux group. We will also study what is flux group in the next few slides. But for the sake of completeness, I have to explain this structure a little bit so that in the subsequent slides you will get it understand quickly. So this is the flux group, which is the precursor for the CME. And precursor means when we study the CME, the main thing, most CME, like 90% of the CME shows is a magnetic loop-like structure, and these are twisted, and we call it the magnetic flux group. And when the CME occurs, we can see there are reconnection happen. This reconnection actually creates number of photons and few uncharged particles. Those are also flare. And at the foot points, due to the aligned magnetic field, few charged particles also emitted from the loop of the foot points. So these 2 points are actually connected. We call it flare ribbon. So soft X-rays are emitted from those flare ribbons. So those X-ray emission is the flare. But when the reconnection occurs, the flux group and the other part will goes up. Those create the CME. So flare is the photon, CME is the plasma blob with some charged particles. Now, what is reconnection? You people may already know it. Reconnection actually when two opposite directed magnetic field lines come close together. There is a Lorentz current, and those Lorentz current keeps those field lines close to each other. You may remember from the Biot-Savart law from class 12 that when two opposite current passes through it, they will attract each other. It's similar like that, since in the ideal MHD, the plasma actually frozen into the magnetic field line, and two opposite magnetic field lines, the Lorentz force occurs and they come close together. And when they come close together, they interact with each other and they change their topology. That's the reconnection. So from this diagram, so the top and the bottom part come close together. They interact with it and then move the right and the left side. So their polarity, which is like top bottom, change to sidewise. So this is the reconnection. So in the reconnection, magnetic topology changes. These are important features we need in the subsequent slides. Sorry. Now flares are associated with the CME, I already told, but there are few cases in which you can saw a CME but not a flare, but not a CME. So when a flare present without a CME, we call it confined event. And when there is a CME as well as a flare, we call it eruptive flare. So you actually can't see a CME without a flare. The reason is that CME always need a reconnection, and when there is a reconnection, there are flares. So CME without flare is quite impossible. At least early days, people believe flares and there are CMEs without flare, but now people understand that at that time the instruments are not so powerful to distinguish the low resolution flaring event. Now, as we go mostly focus in the CME, this is one structure of the CME. CME normally shows three-part structure. One is the leading edge, one is the cavity, one is the core. The leading edge is the compressed plasma materials, and which gives rise the sheath region of the ICME, which actually causes the storm or the space weather impact. The cavity is the magnetic flux loop or the large twisted corner loop, and the core is the prominent material. At the foot points of it, the soft X-ray actually emitted. Now, not all the CME will show this three-part structure, but 30% or mostly 40% of the CME, if you will observe, shows this type of three-part structure. It is not that the other types of CME don't have three-part structure. When we see the CME from the limb, that means when the CME emitted 90 degree of a line of sight, we can mostly see the three-part structure or jet-like structure, which are very less common. But if the CME comes towards us, we can see a blob-like structure like this. These type of CMEs we called halo CME. So this circular type of structure, the reason is that it actually comes towards our planet. So when we see the CME, we can see umbrella-like structure comes towards us. But from the side view of with respect to the CME propagation, most of the time they also show the three-part structure. And these are the classification of CME based on the appearance and based on the speed. CMEs are two types: slow CME and the fast CME. So slow CME means the speed of the CME is less than 400 kilometers, and the fast CME speed is more than 400 kilometers. The specific reason for choosing this 400 kilometers per second is that except the CME and the other thing, sun typically expel a solar wind-like structure. The speed of the average speed of the solar wind is actually 400 to 500 kilometers per second. So, if the speed of the CME is less than the solar wind, we can call it a slow speed. The reason is that since the solar wind is fast, the CME is below it, and the solar wind actually opposes the propagation of the CME. So the CME will eventually go slow. But on the other hand, if the speed of the CME is more than solar wind, so the CME will in front of the solar wind, and sometimes solar wind pushes the CME to gain the further speed. Now these are multi-wavelength observation. So scientists actually send several satellites, and one of the most important is SDO, Solar Dynamic Observatory. And in that satellite, they have two payloads. One is AIA, one is HMI. HMI actually captures the magnetic feature like the radial magnetic field, the poloidal and the azimuthal magnetic field from the Zeeman line splitting. That's what we read in the BSc second year. So the same physics they also used in the payload to capture the magnetic field. The other thing, the AIA, which actually captures these colorful images. So first of all, the sun's actual color is white, not this type of colorful thing. But this proxy color represents different surface of the sun or the solar atmosphere. So at every level of the solar atmosphere, there are different material, there are different elements present, and every element there are some characteristic wavelength or temperature. So those particular temperature shows different levels of the solar atmosphere, and these colors actually represent those different levels. So now we will mostly focus in the physical understanding. So I already said that the magnetic flux rope is the precursor of the coronal mass ejection. So this pink-like cylinder, this pink, not the red one, is the magnetic flux rope. And there are ambient field. The ambient field means the field due to the magnetic activity of the sun, which are above those flux. And these foot points are the different polarity region of the active region. Now, if we split one ambient magnetic field, we will get two types of field. One which are toroidal with respect will create the total magnetic field or ambient field or the potential field in case. Now, in this figure, this pink color is the flux rope. But the definition of the flux rope is that it should be twisted. So it is a rope-like structure which are twisted. Twist means if we I think the most common feature is your mobile charger. Nowadays, people have this kind of braided structure. So the braided structure is actually twist. When you rotate one string-like thing around there, so this will give it twist. So the magnetic flux rope is nothing but the twisted magnetic field lines. Now, this is the schematic view of the cross-section of the magnetic field flux rope. There are different current and magnetic field, like dg. This G means the guide field. Since guide field toroidal with respect to the flux rope, is the toroidal structure. PS is the strapping field which are perpendicular to it. There are internal magnetic field due to the internal current, like PI, which is created due to the poloidal. PI is the poloidal magnetic field, which is created due to the toroidal current, and the toroidal internal magnetic field is created due to the poloidal current. Now, this current, internal magnetic field, and the magnetic field of the strapping of the ambient will give three different which is one force is the Lorentz force due to the toroidal current and the internal poloidal field. The strapping field is the Lorentz force due to the strapping magnetic field with the toroidal current density, and the negative sign represents that this Lorentz force directs downward towards the photosphere. And one tension force, which is the Lorentz force of the poloidal current with the sum of the magnetic guide field and the internal poloidal field. These three forces gives different instability in the solar corona and gives the rise CME. Now, the initiation mechanism for the CME. For every CME, there are three types of things we need. One is the precursor, and I already said that 90% of the CME shows a magnetic flux rope, but still we don't know that there exists prior to it or it formed during the CME. So both of cases people observed, and if they exist prior to the semi, what is the mechanism to get a flux flow before the reconnection? So there are multiple mechanisms, but most of the time there are flux emergence or the flux cancellation. I will not go through more in the detail, but from the term you can understand in the flux emergence, the magnetic flux loop is actually coming from below the photosphere towards the atmosphere, or in the cancellation case, the sunspot is not actually fixed to the sun. They are continuously moving around each other, and they create a shear. And this shear actually gives the cancellation of the magnetic field lines. And for that cancellation, the flux loop are formed before the reconnection at the atmosphere. But after you get the precursor, they need a trigger to imbalance the structure. The trigger is the torus instability or the helical kink instability. We will go into detail in the next slide. So these are remedy instabilities which actually disturb the system, and when it disturbs, the CME initiate, but to sustain that disturbance, we need reconnection. Now, the torus instability and king instability, in the earlier fourth slide, we mentioned this. But in torus instability, the upward force and the downward strapping force, there is a competition between them, and these two force competition gives rise to the torus instability, and their characteristic parameter we call it decay index. And decay index, there is a formula, but I think just keep in mind the critical decay index is 1.5 plus minus 0.2. So suppose in this step you calculate the decay index, and the decay index at a particular distance is less than that. That means the flux loop is torus safe, not torus unstable. So the flux loop is safe, they will not get up. Sorry for that. And the next instability is king instability, which occurs when the current density is large or the guide magnetic field is small. So this current actually causes the outer field line to reach around the row. So these characterized by the twist factor. There is a formula for that, which is the differentiation of the toroidal flux and the poloidal flux, and the critical value is 1.25. So twist is the windings of a field lines around the axis. So if the windings around the axis of the flux loop is more than 1.25, we can say it's a kink instable. So they can show the semi-eruption. So this is one of the slides I did last year. In the cartoon I mentioned there is the current seat. So this is the current seat, and the flux loop is passing through it. So this is the top view when we see from the top, and when we see from the side, we can see this sigmoid-like structure. So this shows there are kink instability of it. Now, the reconnection flux is the flux which are the flux due to the magnetic field lines passing through this reconnection. So first of all, the reconnection seat is a complex topological structure. It's not a straight plane. It's a হ্যাঁ আমার আর 10 মিনিটের মতো টাইম লাগবে ওকে ঠিক আছে ওকে So now we will go further simulation thing. I think these slides are not important, at least these are not. Now we will see some torus instability and their differences. So if we check, so from these two simulation we can see that in the torus instability, there is no wreath-like structure, but in the kink, the flux rope actually winding is around the central axis. And I already said there are flares which show CME, there are flares which are not. This is one of those events. So in confined events, there is flare, but the flux rope will not erupt. But in this case, they will erupt in the right side. I think it will a bit slow, but it will show some eruption in the right panel. Yes, the right panel shows rating, so it's the king unstable. But in the left thing, the flux rope goes down, so it will show a flare, but not the same. Now, those are only for the single CME. We can get multiple CMEs. This is one of my simulation in this case. Two simultaneous CME, and this is first one, and we will get the second one. The second one is, the first one is the partial eruption, and the second one happened at 36. Yes, this is the second one. So we can also get the multiple CMEs, not only two, but we can also get three CMEs too. So these are numerical model, but these are based on observation, not like just few parameters. This will show three CME. It is done by Chatterjee et al. In 2013. Now this is so the CME energetics. This is the kinetic energy of the CME, and this is the magnetic energy. The blue line. Please check the order. Magnetic energy is 10 to the power 31, whereas the kinetic energy is 10 to the power 30. So at the onset of the eruption, the magnetic energy changes, and part of the energy will give the kinetic energy. In this case, there are two CME, so there are two part of it. Now, the reason for the confined and the eruptive CME is basically understood from this diagram. This diagram by Myers paper in 2015. So in this case, when we plot the decay index and the twist, so safety factor is the inverse of the twist. So lower safety factor means more number of turns or the more number of twists in the flux rope. And in this case, we can see if the decay index is large and the twist is large, those so eruptive. If both are small, they so stable. But in this case, when the twist factor is small, but the decay index is large, so at that time we can see that there are few CMEs, but not all of them. So they call it felt torus. And on the other end, not a single event, so CME. So they are felt king. So king is not the most important instability for a flux rope to show a CME. Yes, king can unstable the flux rope, but we need torus instability to observe a flux rope to be a CME. Now, so these are lower coronal study, lower coronal simulation, but the space weather impacts when the lower coronal CME comes to the heart. So this is one of the simulation or mostly prediction by space weather cell of the NASA. They use a code NLIL. NLIL actually predicts solar storm before 4 to 7 days. I start the movie, we can see there is a flux rope. This green dot is the sun and the red dot is the satellite. This is the top view and this is cross-sectional view. And this shows the radial velocity of it. Now, when it comes to the what, it will interact with the our planet's magnetic field. So this is one of the simulation by the visualization cell. So this is one Carrington like event which happened in 1850 and which is the largest coronal mass ejection and the solar storm people know. So in this case, what we can see that when the CME hits, it will interact with the Earth magnetic field and disrupt the Earth magnetic field. Though it is not permanent, after a day or after 6 hours, the Earth's magnetic field quickly reform. So we are actually believed since Earth has a dynamo-like thing and we are resisting the solar storm like explosive events. So thank you. These are the ending slides. This is a smiling sun which we observed on 2022 October.
Thank you, Dr. Samriddhi Shankar Maity. This session is really informative. And do any of you have any question? Okay, I think there are no questions. So I thank you once again, sir. We are really honored to have you among us. Thank you, sir. Thank you. So as we have finally approached to the end, now As we have approached the end, I request the participants to collect your certificates from outside from the desk of registration. I would now like to invite Mr. Mohammad Rafi for the vote of thanks.
Good afternoon, everyone. It's a great honor for me to deliver the vote of thanks on behalf of our Department of Physics, SR Fatehpuria College. I would like to extend our sincere thanks to our esteemed guests for gracing us with their presence and for their inspiring speech. Our heartfelt thanks to all the speakers and the participants who made these events enlightened and memorable. Special thanks to our teachers and students whose hard work ensured the success of this event. A warm thank you to all attendees for being such a wonderful audience and for your support throughout the event. With that, I conclude the vote of thanks. Thank you once again and have a great day ahead. তোমরা তোমাদের সার্টিফিকেট গুলো ঠিক আছে তাহলে মানে আমাদের কলেজের স্টুডেন্ট যারা আছো তোমরা পরে নিয়ে নিও তোমাদের গুলো এখনো রেডি হয়নি নেক্সট যে কোনো একদিন সার্টিফিকেট গুলো পেয়ে যাবে আর তোমাদের ফিডব্যাক জানাবে তোমাদের একটা ফিডব্যাক ফর্ম কি দেওয়া হবে কি করবেন গ্রুপে একটা হ্যাঁ ফিডব্যাক ফর্মটাকে